Okay. Good morning, everybody. Here's my goal. If we finish chapter 19, that's great. Because we'll be ahead of schedule by one lecture. Good thing. It's always good to be ahead. We can always relax and do more homework problems during lecture if we're way ahead. Otherwise, better to be. Anyways, it's better to be early than late. And then we will take quiz number 1 later. I was able to find a calculator, and I have one in my pocket. Someone reserved it from yesterday that they didn't have a calculator. Yeah, I have it. However, I can't guarantee when I find a calculator in a drawer how to operate it. So it's on you. If you forget your calculator and you have one, so I don't know which one you're so comfortable with. So there isn't much, but one of the problems I think you have to solve a quadratic. Oh boy. So yeah. Okay, so let's continue with chapter 19. Chapter 19 was about work, heat, and the first law of thermodynamics, right? And it basically said to change the internal energy or the thermal energy of a gas, you have to add heat to it or do work on it, right? And so that's what we were working with. The work done was what? The work done on a gas, what was the definition of it? Let's just review a little bit. Work was W, right? It's force times distance times the cosine of the angle, but it turned out to be minus EdV, right? That was the work. And then, so work is macroscopic. You're actually doing work. You see a piston moving, somebody's pushing it or something happening like that. And then we talked about heat. Let's see, heat, the symbol for heat was what? Q, thank you. And now, what is heat? It's energy. But more specifically, it's energy that transfers from hot to cold or cold to hot? Hot to cold, higher temperature to a lower temperature. So we talked about heat. We started talking about what heat does. When you add heat to something, it will raise its temperature by a certain amount, depending on the specific heat. We'll do an example in a second. And then the remaining of the chapter, we'll just discuss some more heat of the gases, and then we'll discuss how heat transfers by 3 mechanisms: conduction, convection, and radiation. And the last part, the heat transfer, is probably the least critical part of it. Just certain formulas that you have to apply. Otherwise, the conceptual part is the more important. Okay, so that was heat. We said for solids and liquids, you have the specific heat, right? And it says, so for solids and liquids, you add heat, and if it's in the same phase, if it's, let's say, a liquid, you add heat, the temperature will rise. Let's say it's a solid first. You add heat, the temperature will rise and rise and rise until the solid starts to melt. You reach the melting point. And then any heat you add will not go into raising the temperature, but rather it goes into melting it, right? So you reach a plateau. The temperature stays constant, but it's melting. Your heat is doing something. That's called the latent heat of what?
Fusion.
Of fusion, right? That latent heat of fusion. And then it boils, it becomes a liquid. And then you heat it, the temperature will rise and rise and rise until the liquid becomes what? Vapor, or gas, right? And then the temperature again will start to plateau until the whole liquid becomes a gas, right? And then the temperature of the gas will start to rise somewhat. So if it's in the same phase, if it's not changing phase, then Q was the mass of that sample that you have, the mass of the liquid, times the specific heat, right? Times the change in temperature. And there are tables for specific heats. again, like I usually say, tables are there to look at and consult, right? Not to memorize. If you need the specific heat, you go and look it up at the table. In the test, obviously you don't have the time to look it up. I would provide it for you. And yeah, and so that is that. So let me get to this problem here, and then we'll get to the specific heats for gases. So you take a 200-gram piece of iron at 120 degrees Celsius. So let's see. So take, here's an example. So 120 grams of iron at 120 degrees Celsius. And by the way, the specific heat of iron, I'll just give it to you, 449. 449 joules per kilogram per degree Celsius, or per Kelvin. Right, remember per Kelvin is the same as per degree Celsius, right? Because a change of 1 K is the same as a change of 1 degree Celsius. You've got 120 grams of iron, and then you also have 150 grams of copper at negative 50 degrees Celsius. And the specific heat for copper has the symbol Cu, and it is, specific heat of copper is 385 joules kilogram degrees Celsius, specific heat of copper. And then you also have 100 or 300 grams of ethyl alcohol, So 300 grams at a certain temperature. At 20 degrees Celsius. And then the specific heat for ethanol, I'll put ETH, is 2400 joules per kilogram degrees Celsius. Okay? Now these temperatures, for iron and copper, I'm sure that they're not going to melt, because both of them, they melt at over 1,000 degrees Celsius. Okay, and they're solids already, so they're fine. They're not going to change bit. Ethyl alcohol at 20 degrees Celsius, it's a liquid. However, it freezes at, let's see, it freezes at negative 114 degrees Celsius. So do you think the ethyl alcohol is going to change phase and become a solid? Is it going to freeze? No. I mean, nothing is at negative 114 degrees Celsius. So it's not going to reach that. However, it evaporates, or it becomes, it boils at 78 degrees Celsius. Potentially it could boil, right? So how are we going to approach this? Oh, by the way, the problem is mix all of them up, put all of them in a pot, right? Drop the 120 grams of iron at 120 degrees Celsius, and drop this piece of copper at negative 50, and drop the 300 grams of alcohol, all of them, mix them together. And the question is, what's the final temperature of everybody? They will reach some final temperature. What would be the approach? Now, there are three possibilities. One of them, the alcohol boils at 78. One of them, maybe the final temperature would be less than 78, somewhere between 20 and 78, or somewhere there. It's not going to boil. And that's fine. And then the other possibility is it might be above 78, the final temperature, in which case the alcohol boils, right? Okay. And then the other possibility, you might have it at the boiling temperature. Some of the ethyl alcohol remains as liquid at 78, and part of it will boil at 78. So you got some liquid and some gas. So three possibilities. The other possibility we ruled out, right? The one at negative 114 degrees Celsius where it solidifies. So that one is ruled out. So what's the approach to this? Well, what you have to actually do is you assume the first possibility. You say, you know what, I'm going to assume it's going to be a liquid and see what the temperature I get. If I get a temperature in the range I assumed it to be, then I'm good. If it turns out that the temperature is some weird number that's not in that range, it means your assumption is wrong, and you have to go back and modify it, and then go ahead and assume maybe it boiled, and then take that temperature, and then if that works, great. If it doesn't, you have to go back and modify that assumption and say, well, maybe it's exactly at 78, some of it is boiling, some of it is still liquid. And we're going to do that approach. Well, it turns out you can take a guess. From these numbers here, the way they look like, you got 120 grams and 150 grams, this one is at 120, this one at negative 50. Their specific heats are not that far apart. So the temperature is probably going to be somewhere between these, right? And the 20. So I don't think it's going to boil. That's a good guess. It's good to take just an educated guess to save yourself some time. And it turns out that is the case. Okay, so we're going to assume the temperature is going to be somewhere, I don't know, where ethyl alcohol is still a liquid. So we're going to say, so who's going to lose heat and who's going to gain heat? So which of these will its temperature definitely drop?
Iron.
The iron, yeah, that's the highest temperature it's going to, so the iron will lose heat, right? How about the copper? It will gain heat. The ethyl alcohol, we're not sure. It could possibly be at 15 degrees, lowered a little bit, or in that case it will lose, or it could gain energy, gain heat, and then become at 25 or 30 or 40 or something like that. So we're just going to call the final temperature of T final and then see what happens. Now, the heat lost would be a negative quantity. The heat gained would be a positive quantity. So if I add the total heat of my closed system, the gain plus the lost, what's the total? It would be zero, yeah, it would be zero. Right? Let's say the iron loses 5 joules, so that's negative 5 joules, and the copper gains, let's say 3 joules, and the ethyl alcohol gains 2 joules. So that's a loss of 5 and a gain from the other two of 5, and so it would be a 0 at the end. So that's what we're going to say. We're going to say 0 is equal to. We'll start with the iron. So it would be the mass of the iron times the specific of the heat of the iron times the change in temperature of the iron. So the mass of the iron is what? I'm going to plug in numbers because it's there is only one unknown, and I'm going to just plug them in right away. So what's the mass of the iron? 120 grams. The specific heat is something per kilogram, so I better change this to kilograms, right? So 0.1. So 0.1 times the specific heat of iron. Again, we said it's 449. And then times the change in temperature. Change is always what? Final minus initial. Thank you. So it's going to be the final temperature. I'm going to just call it T minus the initial temperature. The initial temperature is 120, right? And you see already this number will probably be negative because T will be less than 120. So let's say it's 50. So 50 minus 120 would be like negative 70. So this quantity will be negative. Okay. So plus, we will do the copper now. The mass of the copper is 150 grams, so 0.15. Specific heat of copper is 385. And then the final temperature minus the initial temperature, T final minus the initial temperature. That's negative 50, right? So make sure you put minus, because the temperature is negative. So minus is a plus, yeah, agree.
Do you convert to Kelvin here or in?
What do you think? Should I convert or should I not?
Oh, it's in degrees.
It cancels anyways, right? If we add 273 to this temperature and add 273 to this one and then take the difference, it doesn't matter, yeah. So whenever you take the differences in temperature, you don't need to change the Kelvin. Because the value that you add will cancel. That's a good question. And now the ethyl outcome. So plus, the mass is 300 grams, so 0.3 kilograms. 2400 for the specific heat. And then T final minus T initial, which is 20 degrees, right? So I only have one unknown. And that one unknown is T. Solve this. I let you solve it. You should get, I'll tell you the answer. The 25.7 degrees Celsius, approximately 26. Yeah.
If this were a test question, could we leave our answer in Celsius, or would we have to convert to yen?
I mean, usually you're told you will be provided like T equals something like that. That's typically how I write my quizzes or tests. Yeah. And again, in a cheat sheet or something, do not write like tables of specific heats and stuff. It is provided for you. Okay? Don't try to like write tables in there. It's information that I will give you. If that's okay, I'm going to now go to specific heats of gases. Now, the specific heat of a gas is tricky because I can add heat to the gas. I can lock its volume, right? I can lock it to make sure the volume just stays constant, and I add heat to it. Okay, and I will get a certain temperature rise per so many joules I put in. Or I can let the volume free to change. And then when I add heat, it might expand. And its temperature might rise, and then it will expand. So in that case, not all of my heat goes into raising the temperature. Some of the heat goes into the gas expanding against the rest of the world, against the atmospheric pressure. So let's say if I add a joule of heat, it will not give me the same rise in temperature for the two different processes as constant temperature, constant pressure or constant volume. Which one will give me a greater rise, do you think? Which one will, like, I get more, what did they say? More bang for your buck, right? Which one will give you more? I put some heat in and I want a bigger rise in temperature. Is it the one where I lock the volume or the one where I let it expand?
When you lock it.
Constant volume, yes. In that case, every heat you add, the volume is locked, so it's not going to do work against the world. Because when the gas does work, it's doing positive work. It means the world is doing negative work. So you're losing energy from work, doing work, instead of using that energy to increase your temperature. So the specific heat at constant volume will be less than the specific heat at constant pressure. Because a small amount of heat with constant volume will have the same effect as a little bit larger amount of heat at constant pressure. So let's see here. I put some values here in the table, from a table in our book. So it's called the molar specific heats. They are in joules per mole per Kelvin for a gas. Cp is the specific heat at constant pressure. It's called the Cp. Cv is the specific heat at constant temperature. Let's just write it down. So remember, Q was the mass times the specific heat times delta T, right, for solids and liquids. So for a gas, instead of speaking of the mass of the gas, what is it more useful to speak of? Yeah, the number of moles. Or volume, you can have more molecules packed in there, right? So I care about how many molecules there are, right? Because that's directly related to the mass. The mass would be the number of molecules times the mass per molecule that will give you the total mass. So I want to, for gases, it's better to speak of the number of moles. So it would be the number of moles. And then the specific heat here, instead of, look at this one here. Earlier, when we had the mass here, specific heat was measured in what? Joules, degrees Celsius, but per kilogram. But this one, since I'm working with moles, it would be joules per degree Celsius or Kelvin. But instead of per kilogram, it would be per what? Per mole.
Mole.
So, the molar specific. So it's, instead of the mass, I would have N, and then the specific heat times delta T. Now again, the specific heat I have to specify. Is it constant volume, constant pressure? Cv is the specific heat at constant pressure, a constant volume, sorry, volume. And Cp is constant at constant pressure. We will derive a relationship between them soon. Notice these, are these monatomic or diatomic gases?
Monotonic.
They're monatomic. Good. They just have one atom. These are diatomic, right? What do you notice about the, let's consider the monatomic first. Their specific heats, Cp for example, they're all similar. In fact, the way they're the same. They're the same specific heats. Cv is also the same, right? Cp, Cv, there's for all of them, right? As long as it's monatomic, the Cv or Cp is the same. Notice the difference between Cp and Cv. What do you get?
8.3.
8.3. What does 8.3 remind you of?
Universal
R.
gas.
R, yeah. So Cp is larger than Cv as we expected. It takes more energy to raise the temperature at constant pressure than constant volume. That's why the specific heat is larger. The difference between them is basically the R value, 8.3. Diatomic, specific heats are about what? 28.7, 29.1, 29.2, and then the Cv is like 20 something. Again, the difference is 8.3. 8.3. Now, if you go ahead and figure how many multiples of R is Cp and how many multiples of R is Cv, Cv looks like 1.5 R, right? 1.5 times the 8.3. So that's 3 over 2 R. 3 over 2, right? Because if you take R and multiply it by 1.5, you get about 12 something. For Cp, it's about 2.5 times. If this one is 1.5, this one is 2.5. Because the difference between them is 1 R, right? For this, it looks like these values are these values, right? So for diatomic, this one is 2.5. This one turns out to be like 3.5. Yeah. Okay. We'll see this in a little bit. Yeah, so that's that. Any questions on this? What specific heats? Yeah.
Just remember, the specific heat refers to the amount of heat needed to change it from one phase to the next.
The specific heat is the amount of heat needed. In this case, for example, to raise the temperature of 1 mole of gas by 1 degree
Okay,
Celsius.
right.
Or 1 Kelvin.
Yeah.
Yeah. So yeah. So let's do an example just to get a feel for this. And the example is from the book. It says, suppose you have 3 moles of oxygen. So here is the example. Always have trouble writing here. So consider 3 moles of O2. 3 moles of oxygen. It's a diatomic molecule, right? So if we need specific heat, we're going to use these of O2 at, let's say the O2 is at 20 degrees Celsius. Initially it's 20 degrees Celsius. We're going to put in it 600 joules of energy, of heat energy. So first, input or put in, so we're going to add input, maybe the word add is better. So first add 600 joules of heat. So if I say we added 600 joules of heat, what's the final temperature of oxygen, of O2? Is that a complete description, or I need to give you some more information? What is the information that you need?
Volume or pressure.
Yeah, am I adding this heat at constant volume or at constant pressure? Yeah, good. So we're going to add this heat at constant pressure. At constant pressure. Okay. And then, next, we're going to we're going to remove 600 joules of heat at constant volume. Next, we're going to remove 600 joules of heat at constant volume. The question is, find the final temperature. So as you expect, when you put 600 joules of heat at constant pressure, the temperature is going to rise. And then when you take out the 600 joules of heat, the temperature is going to drop. But because we have 2 different processes, you probably wouldn't have the temperature at 20 degrees again, right? Not just because we put in 600 and then we put in and then we took out 600, it's going to end up at the same temperature. Yeah. So what's the final temperature? Find T final. Find the temperature at that. Find the temperature at that. So we're going to do exactly what we have here. One of these. So the first process. So in number 1. In step 1. Step 1, it's constant pressure, right? Constant pressure. So I know that Q is equal to N CP or CV? P, right? Because it's pressure, constant pressure. Times delta T. Times delta T. What do I know? Do I know Q? Yeah, we added 600 joules, so positive 600, so 600. Do I know N, the number of moles?
Yes.
How many?
3.
We have 3. It's, yeah. Do I know CP?
Yes.
Yeah, it's oxygen, so what does it say? 29.2, right? For oxygen, according to this. Yeah, 29.2. Hopefully I copied them right. So we'll see. 29.2. And then delta T. T final minus T initial, right? Change in temperature. So T, let's call it, since it's the temperature at step 1, and call it T1 minus T initial, which was 20, right? 20. So let's find T1. So divide by all that and you get T1 is 26.85 according to my 26.85. Is this okay? All right. So now step 2, we're going to remove heat now at constant volume. We're going to remove heat. So the equation would be Q equals to what? N what? Yeah, CV is constant volume times delta T, right? So what should I put for Q? Thank you. It's a negative. Yeah.
Never mind. Never mind.
Okay. So Q now, because we removed 600 joules, so minus 600. N is 3 still, right? CV for oxygen is this one? 20.9, right? 20.9. Delta T will be T at step 2 minus T at step 1, right? Which is 26.85. 26.85. Sorry, my space is running out. So P2 would be 17.28. That's when it is. So now, does this make sense? Does it make sense that it's actually lower than 20? It actually does make sense. Because the 600 joules you put first at constant pressure, not all of it went into raising the temperature of the gas. Some of it went into expanding. The gas was expanded. So it did work pushing the atmosphere out, right, the piston out. And that's work that you're not going to get back. So that's gone, so it expanded, you lock the volume, and now you take out 600 joules of heat at constant volume. That has a larger effect, so it drops the temperature more than it raised it at first. So you end up with less than 2. If you're not sure, this is the calculation. Okay. Now, I want to show you the relationship between CP and CV. I thought we were going to get to the adiabatic process, maybe, but we'll see. We're still on schedule. So let me, so the relation between CP and CV. We already know the relationship between them. CP minus CV is R. But I want to show you from using the ideal gas law and the first law of thermodynamics that that's the case, right? So we want to show that. So here is the PV diagram. Here's P. An isothermal process, how does it look like? So let's say I have a gas at this temperature, at this volume and pressure, and I take it to this one. How do they connect with each other as an isothermal?
Curve?
It's a curve, yeah. It's 1 over, right? 1 over V. It's an inverse. Why? Because PV equal to nRT, right? Yeah. PV equal to nRT. So P will be nRT over V, right? If T is constant, then the V is inversely proportional to V. So P is inversely proportional to V. So it looks like this. Something like that. Okay. And let's say I draw another isothermal process. So which temperature is higher? The lower, this one or this one? The lower curve or the higher curve? And how do we know? Right? This is isothermal, means the temperature doesn't change. And here's another isothermal process. Let's say I went from here to here, this one went from here to here. Which one has a lower temperature? The lower one? Yeah. Let's rationalize one. You're right, yeah, the lower one has the lower temperature. The reason is this. Think about, let's take draw a line like that. Take this point and this. We said this point is at the same temperature as all of these, and this point is the same temperature as all of these, because this is an isothermal process. So why does this point have a higher temperature than this? Well, I know that the temperature is PV over NR, right? If I solve for T, it's PV over NR. NR is a constant. So the product of PV, if it's larger, will give me a higher temperature. So V here is the same as V here. But P here is higher than this. So PV here, this product, P times V, is larger than PV here. Does this make sense, or I'm just talking to myself? It does. Okay, good. All right. So this is a larger temperature. This is the higher temperature. So let's go. Let's say we take process A. Let's say we start here, and process A is going to take us from here to here, like that. That's process A. It's going to take us from this temperature to this temperature at constant volume. Process A is isochoric, right? And let's take another process called process B that will take us from this temperature to this temperature. So what's the same between process A and B? What is the same? The starting point is the same. How about the final point? What's similar between this point and this point?
Pressure.
The pressure is different.
Temperature.
Huh?
Temperature.
They have the same temperature, right? We said this is an isotherm. So if I go to this, as long as I hit this line, or I hit this line here, they have the same temperature. Okay? Is that clear? Okay. So this one I'm expanding at constant pressure. This is constant pressure. And this one is
Constant volume.
constant volume. So the temperature in both processes rose. So what happened to the thermal energy? Does it increase, decrease, or stay the same? The temperature is higher.
Increase.
The thermal energy increases, yes. Thermal energy, the only way thermal energy changes is the temperature changes. If the temperature remains constant, thermal energy is the same. So since both processes, the thermal energy increased, then both of them, the change in thermal energy is actually the same. Because the thermal energy initially had a certain temperature, and then now you have a certain temperature, so the change in thermal energy is the same. Okay, so I'm going to say this. I'm going to consider, let's write down the law of thermodynamics, the first law. The change in thermal energy was what?
Work plus C.
Work plus C, thank you. The work plus Q.
Yeah.
Yeah. Okay, so process A. What do we know about the work done in process A? How much work is done in process A? Zero. Why? The volume doesn't change. Remember, if you don't change the volume, there is zero work. So let's, in process A,